Hello, welcome back. I'm Dr. Bettina Heinz to give you some more instruction in chemistry. Remember last time we talked about the gases. We covered part 1 and part 2, and today we will continue with the gases. We will now discuss gases part 3, which will deal with the ideal gas law. And we see here our cover slide. And these are the topics that we will discuss today. We will discuss the Avogadro principle and the ideal gas law. That is a result of Boyle's, Charles, and Gay-Lussac's law. So including Avogadro's principle with the relationship between volume and moles, we can formulate the ideal gas law. We will also learn about the ideal gas constant, the modified ideal gas law that allows us to determine molecular or molar mass, rather. And we will also modify the ideal gas equation to cover the situation of the so-called real gases, the actual gases. Remember, all these laws dealt with the ideal gas, meaning almost the perfect make-believe gas. And this leads to what we call the van der Waals equation that introduces correctional factors such as A and B constants for the various types of gases that allow us to also do calculations with real gases. This is called the van der Waals equation, and it is needed because of the intermolecular forces involved between the so-called real gases. So there is no minimum of force between the individual particles. We're back into the real world with the van der Waals equation. Now we will talk about the law of combining volumes, which was studied by Gay-Lussac. He did a lot of travels in his hot air balloon and could do some excellent experimentation up there. And he noticed that when gases combine, they combine in ratios of volumes. And that was very interesting. And if we look now here on our slide here, we can see that the coefficients of the balanced equation with gas reactions correspond to the volumes. So when hydrogen reacts with oxygen to make water, then it's actually 2 volumes of hydrogen react with 1 volume of oxygen to produce 2 volumes of water vapor. And this volume can be anything. It could be milliliters, it could be liters, it could be gallons, whatever. But they always are in the same whole number ratios reacting with each other. Another example would be ammonia production with nitrogen gas and hydrogen gas. So it would be 1 volume nitrogen gas and 3 volumes hydrogen gas to produce 2 volumes of ammonia vapors. Of course, this only applies when the external conditions are consistent, unchanged, at constant temperature and pressure. Now, the interesting thing is that Avogadro derived from this was that these equal volume ratios also connect to the same number of particles. And that's the key issue here with Avogadro's principle. That means every volume corresponds to the same number of individual gas particles, regardless of what kind of gas it is. And of course, given that T and P are constant. So we can say, according to Avogadro, that the volume is proportional to the number of moles. The little n stands for number of moles. So you can say 1 mole of a gas occupies the same space at STP conditions as we would now formulate it. Remember, STP means that the standard temperature is 0 degrees centigrade or 273 Kelvin, and pressure is 1 atmosphere. And at that condition, we can say that 1 mole gas occupies exactly 22.4 liters if it's a perfect gas. If it's a real gas, it will be less than 22.4 liters. So real gases are the ones that are heavier in mass and therefore have more polarizability, more intermolecular forces, etc. So regardless of what gas we're dealing with, 1 mole always means 22.4 liters of volume will be displaced. And also, this molar volume will contain the Avogadro number of individual gas particles, which is the Avogadro number, or capital Na, subscript A, which I haven't written here, but that's how we define it. 6.022 times 10 to the 23rd power of individual particles, whether they are molecules or atoms. Doesn't make any difference here. That is called the Avogadro number. And here we see on our PowerPoint presentation, we see Amadeo Avogadro, who was an Italian lawyer at first, but then studied mathematics and physics, and was termed to be a natural philosopher, like people in those days were usually considered to be, instead of a particular discipline like chemist or physicist. We were called, or the scientists were called, natural philosophers. Now, Avogadro didn't have it easy to be accepted. And he had a lot of critics, which, of course, prevented science from progressing. Here we have another overhead, or illustration, that will show how Gay-Lussac, who was very daring, went up to 7,000 meters in the atmosphere to do his experimentation. He produced hydrogen gas with the reaction zinc plus HCl, which will give hydrogen gas, which of course could be ignited by the air or with the help of some activation energy, and the heat produced will produce hot air, which gives the balloon a lift. Avogadro said, remember, that at same T and P, all gases have the same volume and the same number of particles. That was the key point. So equal volumes, regardless of what gases we're dealing with, always contain the same number of particles. And remember, the molar volume has 6.022 times 10 to the 23rd number of individual particles. This is called the Na, the Avogadro number, which Avogadro himself didn't calculate, but his principle helped establish this fact. Now, of course, the scientists were very critical of this at first. For instance, even Dalton said, how ridiculous, I can't accept this. Gay-Lussac didn't like this result either, Berzelius and others, and it took 50 years for this idea to be established again. So people started looking at Avogadro's concept and they said, well, maybe that isn't so bad after all. Like Cannizzaro in 1860, so it's practically 50 years later that this idea was accepted. Now, with all this information, we can get ready to establish the ideal gas law equation. Now we have Boyle, we have Charles, and now also we have Avogadro. That means volume is proportional to the number of moles. We don't really need Gay-Lussac here because the three variables are already established by Boyle and Charles laws. So if we combine everything, then we can say the volume is proportional not only to the number of moles, but also the temperature and inversely to the pressure. If we leave these multiplication signs out and just use the contracted way of writing an equation, then it would be volume is proportional to moles, temperature over pressure. Now, in order to make an equation, we have to have a proportionality factor, and that's usually a constant. And this constant has to have the units incorporated, so when you calculate with an equation, the units cancel in the appropriate manner depending on what you're looking for. So we can say PV, we take pressure on the other left side of the equation. We have PV equals constants times number of moles times temperature. Or PV equals K, general letter for a constant, representing a constant, is N times T. The constant received then the letter R, meaning it stands from now on to the universal gas, for the universal gas constant. So K is now big R, and that can be calculated easily out of standard variables for pressure, volume, N and T. So for STP conditions, remember what STP conditions were? 1 atmosphere for pressure, 22.4 liters for molar volume per mole, and 0 degrees centigrade, which has to be converted to Kelvin, which is 760. And if we compute that, we get 0.0821 in a rounded form for R. So it's called the universal gas constant. Very helpful. And if we now combine all this together in one handy equation, we have PV equals nRT. And this is called now the ideal gas law. And we can work it out in any way we want. We can look for pressure when volume, moles, and temperature is given. We can look for the number of moles. We can look for the volume. We can look for the pressure. We can look for the temperature. R is always a given. However, the value, the numerical value for R can vary because it can be derived from different units like pascals or torrs. But if you use atmosphere, liters, mole, and Kelvin, it always comes out to 0.0821. Now, one thing which is interesting is that we can use this equation to modify it a little bit, because remember the number of moles is any mass divided by the molar mass, grams over grams per mole. If we substitute little n for little m, which is any mass, divided by big M, which is the molar mass, then we can actually have a handy equation that allows us to determine an unknown molar mass of a gas that we might collect in an experimental procedure. So if we measured out how much is produced in grams, and we have all the other parameters established, then we can calculate the molar mass of an unknown gas. So that is very handy as well. With this, we can conclude the ideal gases. Now comes something very important, and that's the intermolecular force that we neglected before, but which is really something to be reckoned with. So I'm going to show you a little model set here that will explain this idea. For instance, let's say the gas molecules are very big in comparison to smaller ones. Then, of course, we will have more attractive forces between the big molecules than the small molecules. This is called polarization, or an induction of a temporary dipole, because when they get close to each other, they can polarize each other in such a way that they become a little oblongly shaped. And notice I've written down delta minus and delta plus. That means the electron cloud of the gas is now not concentrically distributed around the nucleus anymore, so we have a slight separation of the charges. So we have where the electron density is the highest, we have the delta negative end. Where it's a little depleted, we have the delta positive end. So we have an intermolecular force holding the molecules together. Now, the smaller they are, the less intermolecular forces we have. However, we have two forces nonetheless to be reckoned with at all times, and that is a long-range attractive force and a short-range repulsive force. So there's forces to be reckoned with, as we can see, and these are called, all in all, intermolecular forces. And this leads us to the van der Waals equation. And notice we still have P and V, and we have RT and N. Everything is the same as before, except for some van der Waals constants, correctional factors, that have to be considered. Because the volume will be a little bit contracted because of the attractive force. The pressure, we would say the pressure might be less because of the intermolecular forces keep the molecules from bombarding the container wall with the same intensity. But since the masses are bigger, there's sort of a compensation for the lower velocity that is related to the increase in charge. So we can say A over V square is the correctional force or correctional factor for the pressure, and B is the correctional factor for the volume. Now if A and B become 0, guess what? Then we have the ideal gas equation back. These factors are determined for all gases, so we can look them up in the reference tables if we need to do some calculations. If you look at this graph here, these are called PV isotherms. That means the temperature is constant. In the ideal gas, we have a nice slope here, or a nice curvilinear relationship. But when we get more and more to the real gas, we have a little hump here, a little plateau. And that is where the irregularity comes in of the real gas. Now I want to show you something quickly, what the correctional volume means. Let's say we have here a bottle, and we have big molecules in here, and you look at the so-called negative space of the bottle, then there's not that much volume left, right? And if we put the little pink spheres in here, then we notice the negative space of the bottle, or the actual volume of the bottle, is bigger. See, that's how we understand the correctional factor of the volume. Here are some constants for A and B. And you see helium is very, very almost 0 because it's practically a perfect gas. Neon somehow is a little irregular here. It's a little high. And argon, krypton, xenon, you see they get bigger and bigger. And that means they are more easily polarized. And here we have the Bs. Here, I'm sorry, the neon is irregular. See, the helium is larger than the neon. The trend is normally going to bigger values, but you see here neon is a little unusual. So we have monatomic gases, diatomic gases, and polyatomic gases. The biggest number that I see here would be carbon tetrachloride, real heavy gas. And A would be maybe, look at chlorine gas is pretty heavy, but here carbon tetrachloride definitely also the highest number in our setup here. So you see we have covered the ideal gas law, we have covered the van der Waals gas law, and now we will look at some interesting things that might entertain us a bit. Let's look at the properties of gases. As a review, gases have an extreme low density, makes sense. Easy miscibility, that means diffusion and effusion is very easily done. That means they penetrate each other's space readily. Easy compressibility, they're buoyant, so you can push them down and expand them. High degree of freedom and kinetic energy. They occupy every little space of the container and collide with the container walls with equal pressure throughout. And they can be liquefied if we have the right conditions. Now, it's not as easy as one might think. One needs what we call the critical pressure and the critical temperature. What does that mean? You have to slow the gas particles down enough so when they get close to each other, they linger a little bit to polarize each other's electron clouds so that we get an instantaneous dipole. Once the pressure or the temperature is low enough, then you can turn on the thumb screws, so to speak, or increase the pressure that will leave the gas particles close enough together for the critical time to become liquefied. It's all a question, again, of intermolecular forces. Another interesting thing that we can talk about before concluding today is Henry's law. That's sort of an interesting law that deals with the solubility of a gas. And it's interesting to point out here that the solubility increases with external pressure. So the more pressure, the more soluble a gas is in a certain liquid. Now this is very important for the condition called the bends. For instance, a diver will have a problem when he or she is at lower depths, at extreme depths, because the nitrogen will be more soluble in the circulatory system. The air tank will provide the nitrogen, of course, because nitrogen is about 75% of air. So nowadays we use more oxygen and helium mixtures. Now what happens if the person, the diver, rises to the top too quickly? Then we get that terrible condition called the bends. That means the nitrogen at lower pressure levels of the sea will try to get out again, try to escape, and the fastest way is going through the skin. So the skin will be very bubbly and have all these little funny protrusions being visible. Now if that happens too fast, it can be deadly. So that's why today we need to do a gradual decompression of the diver coming back to the top. One more thing that we would like to talk about today is, since it has to do with the gases, it's an application of the gas laws. Liquid nitrogen production, very important today. Liquid nitrogen has many uses. Remember, it's liquefied in the normal procedure. By the way, we call that the Joule-Thomson effect. Extreme expansion of a gas leads to a cooling of temperature. And doing that in a cyclical way, we can liquefy air and nitrogen. It is used for storage of sensitive foods and products that are liable to decomposition. So one produces sort of a liquid nitrogen cushion around the products. It's also used, liquid air for instance, for the removal of warts. Nowadays they advertise do-it-yourself kits, so you don't have to go to the doctor to get your ugly warts removed anymore. And also for storage and freezing of cadavers and organs, etc., biological specimen, etc. Now, we would store bodies for the purpose of future medical applications, treatments, or just to preserve a cadaver for the medical school, for instance. So here we see how air as a gas, first we remove the CO2 and the water, then it just has the nitrogen and the oxygen and the other inert gases in there, and then lowering of pressure, cooling, repeating this a few times, we get liquid air and nitrogen. Now this is quickly how a body is preserved. The water is removed. It is stored in ethylene glycol, which is antifreeze. Then you put a plastic wrap around it, put it in the ice bath. Ice and salt can also lower the temperature below 0 degrees centigrade, below the freezing point of water. Then you wrap the whole thing up in aluminum foil, and then it's submerged into a dry ice, and then a nitrogen cushion that preserves the body until a treatment for the condition, the medical condition, is found. And that is the method they use in the cryonic society. Costs a lot of money to belong to that. If you want to be frozen, it costs an awful lot of money, but it can be done. I don't know if it'll work, but it's definitely some hope. And anything else can be stored that way. So the Iceman of Austria, the prehistoric man, was probably also stored in this manner. So I would like to come to a close now. We have hopefully learned enough today so that we can continue with gases 4 in our next episode. So practice some of these problems using the ideal gas law, modified gas law, and Van der Waals law. And thank you very much for paying attention. And I hope I kept you interested, and I hope you enjoyed learning this material. Gases are a little extensive, but very important, but very straightforward. With this, I would like to say goodbye and hope to see you next time around.